What if I told you there are bridges that don't just span rivers, they carry them? Think about it. Water flowing through the air, boats sailing over highways, and canals crossing other rivers. These water bridges flip the traditional idea of a bridge upside down, and they've been solving impossible challenges for centuries. But how do they work? And why would anyone even build such a thing? Let's find out. Long before cars and trains reshaped the way we moved goods, waterways were the arteries of commerce. During the Industrial Revolution, roughly from the 1760s to the 1840s, canals transformed transportation. Imagine this. A single horse walking along a canal towpath could haul up to 30 tons of cargo, something unimaginable on land. Entire canal networks were designed with horse-drawn boats in mind, featuring smooth curves, carefully maintained towpaths, and even posts for strapping ropes during sharp turns or stops. This simple but transformative efficiency led to the construction of thousands of miles of canals, with Britain spearheading the movement, creating a vast network stretching over 4,000 miles, about 6,437 kilometers. But as these canal networks expanded, they ran into a fundamental challenge: how to maintain a steady flow of water across valleys, rivers, and other obstacles. These weren't minor inconveniences, these were natural barriers that could halt the entire system. The solution? Water bridges, or as they're often called, navigable aqueducts. The idea was bold. Instead of letting rivers disrupt canals, engineers decided to carry the canals over the rivers. It was a feat of engineering ambition, and early pioneers rose to the occasion. In the late 18th century, Britain saw the rise of remarkable structures like the Lune Aqueduct and the Edstone Aqueduct. Using advanced masonry techniques and early forms of waterproofing to create channels that could hold water and carry boats high above the landscape. The success of these aqueducts wasn't confined to Britain. Inspired by their ingenuity, the concept spread globally. In the United States, for instance, canals and aqueducts connected the Great Lakes to the Atlantic Ocean, opening up vast inland regions to trade and development. Today, modern water bridges like the Magdeburg Water Bridge in Germany continue this legacy of solving the same age-old problem: carrying water, and the boats that sail on it, across landscapes that would otherwise stop navigation. Located in central Germany, the Magdeburg Water Bridge spans the Elbe River, connecting two different canals and merging them into one massive aqueduct that stretches 918 meters, just over 3,000 feet, with a width of 34 meters, 111 feet. It stands as the world's longest navigable aqueduct. Its water depth of 4.25 meters, 13.9 feet, ensures that even large commercial vessels can cross with ease. Before the bridge was completed, ships had to take a 12-kilometer, 7.5-mile detour to cross the Elbe River, saving time and fuel, making it a vital part of Germany's inland waterway network. Built between 1998 and 2003, the project required 24,000 tons of steel and 68,000 cubic meters, about 2.4 million cubic feet, of concrete. Over 1,500 workers brought this structure to life, completing it at a cost of 501 million euros. On the one side, we have the Magdeburg Water Bridge, a record-setting giant of size and scale. On the other, there's the Veluwe Aqueduct, officially the smallest navigable aqueduct in the world. This compact but ingenious structure in the Netherlands proves that big impact can come in small packages. Located in Harderwijk, this aqueduct connects mainland Netherlands to the province of Flevoland, serving as both a waterway for small boats and a crucial highway crossing. At just 25 meters, 82 feet long and 19 meters 62 feet wide, the Veluwe Aqueduct is tiny compared to its counterparts, but don't let its size fool you. Before its construction in 2002, alternative options like tunnels or drawbridges were considered. Both proved far more expensive and less efficient. The aqueduct, on the other hand, offered a cost-effective solution. blending functionality with a design that seamlessly integrates into the natural landscape. And it's not just about boats. Beneath the aqueduct's waters flow 2 busy lanes of road traffic carrying up to 34,000 vehicles daily. But the real beauty of the Veluwe aqueduct lies in its simplicity. With a water depth of just 3 meters, 10 feet, it supports the passage of small boats and yachts, ensuring uninterrupted maritime traffic while keeping vehicles moving below. Another engineering gem is the Barton Swing Aqueduct in Greater Manchester, England, the world's first and only swing aqueduct. Built in 1893, this Victorian marvel carries the Bridgewater Canal over the Manchester Ship Canal, rotating 90 degrees on a central pivot to let large ships pass below. Stretching 330 feet, 100 meters, and weighing 1,450 tons, it holds 800 tons of water during operation. Designed by Sir Edward Leader Williams, the aqueduct features a unique system of 64 tapered cast iron rollers, originally powered by hydraulic steam engines before switching to electric pumps in 1940. Remarkably, it still operates today, showcasing the enduring brilliance of Victorian engineering. In central France, the Brière Aqueduct stands as a stunning blend of engineering and artistry. Built between 1890 and 1896, this aqueduct was a collaboration of brilliant minds, including Gustave Eiffel, the engineer behind the iconic Eiffel Tower. Eiffel designed the stone foundations. Stretching an impressive 662.7 meters, 2,175 feet, and holding 13,000 tons of water, the Brière Aqueduct was the world's longest navigable aqueduct for over a century. Supported by 14 piers, it replaced a dangerous river-level crossing and connected the Loire and Seine river systems. Its design wasn't just practical. Decorative lanterns and ornamental columns inspired by the Pont Alexander III in Paris elevate it to an architectural masterpiece. Next in line is the Pont Kisichte Aqueduct. Completed in 1805, this aqueduct was designed by the legendary Thomas Telford and William Jessop as part of the Ellesmere Canal project. At 38.4 meters, 126 feet, it holds the title of the world's highest canal aqueduct, earning it the nickname the Stream in the Sky. Spanning 307 meters, 1,007 feet, with a water depth of 1.6 meters, 5 feet 3 inches, the aqueduct features 18 stone pillars supporting a cast iron trough. Its construction employed groundbreaking techniques for the time, including waterproofing the canal bed with Welsh flannel and a unique lead-iron sugar mixture. A cantilevered iron towpath replaced the original wooden design in 1831, and you can still see rope marks left by horse-drawn boats today. Built at a cost of £47,000, around £4.8 million in today's currency, this UNESCO World Heritage Site is a Grade 1 listed building and a triumph of early industrial engineering. We've seen some of the most fascinating water bridges from across the globe, each unique in its design, history, and purpose. But when we think of bridges, we picture structures crossing over rivers or valleys built to support cars, trains, or people. But water bridges flip that idea on its head. They carry water over the very things we usually expect bridges to avoid. It's an engineering paradox that seems to defy logic at first glance. So, how do these incredible structures work? Imagine trying to lift an Olympic-sized swimming pool filled to the brim with water. That's essentially what these water bridges do, but on a much larger scale. The secret lies in spreading out the weight. Just like lying flat on thin ice spreads your weight so you don't fall through, these bridges use arched supports or specially designed foundations to evenly distribute the immense load. This way, no single part of the bridge has to carry more than it can handle. Modern bridges even use pre-stressed concrete, which acts like a tightly coiled spring to handle the weight more efficiently. The result? Some water bridges can hold up to 80,000 tons of water without breaking a sweat. Now, you might wonder, what happens when a giant ship crosses a water bridge? Wouldn't that add even more weight? Surprisingly, the answer is no. This is where physics, specifically Archimedes' principle, comes into play. When a boat floats, it pushes aside its own weight in water. So whether the bridge is full of water or full of boats, the total weight stays the same. It's like a perfect balancing act that keeps the bridge steady whether it's empty or carrying vessels. But building a small river hundreds of feet in the air can be tricky. In the 1800s, engineers got creative, using materials like lead sheets, boiled sugar, and even Welsh flannel to seal their aqueducts. Today, we rely on waterproof concrete and precision-engineered joints to keep the water in. These materials are so effective that even under tons of pressure, not a single drop escapes. Water doesn't like to stay still, and that's another challenge for these bridges. If the water flows too fast, it could damage the structure. Too slow, and boats would have trouble navigating. Engineers solved this by creating an almost invisible tilt in the channel, just enough to keep the water moving smoothly. Think of it as designing a water slide for boats. The slope has to be just right, not too steep, not too flat. When you put all these solutions together, you get something extraordinary. A bridge that lets water and boats sail through the sky. It's a perfect combination of science, creativity, and ingenuity. Hopefully, now you know how water bridges look so cool above water while holding all that extra weight. Which one was your favourite? Share your thoughts in the comments. We'd love to hear what you think of these incredible feats of engineering. Thanks for watching it, and don't forget to like, share, and subscribe for more MegaBuild stories. See you in the next video.